So this is the extra session in which we will go through every week. We will decide and we will discuss slightly from every week what we had gone through. So I will be just going through all the 12-week presentations one by one and what we discussed in those weeks. I will just repeat that. Okay, let's start with week one. Okay. Okay, so in the first week, we started with KCL and KVL, and this is the first circuit where we discussed what is KCL and KVL. So KCL is a current law which tells us that the current coming to the node, I will be using green marker. No, let me use blue marker to point where okay. So this is the current law that the current coming, that is here I1, I2, and I3, it should be equal to the current leaving. Here the current leaving is 0, so it should be I1 plus I2 plus I3 equal to 0. This follows the principle of conservation of charge. Okay. Then we have voltage law, which says that the total voltage across the loop is 0, and it follows the conservation of energy. So if I look at this loop, so what I will have is you have a potential here V0, then you have a potential drop of V1 and V2, and it will be V0 is equivalent to V1 plus V2. So this is from, if I multiply both sides with Q, so it becomes energy E0 is equivalent to E1 plus E2. So it follows the conservation of energy. Okay. So if I now look at the circuit, what I can do is I can use both KVL as well as KCL. So when I have to find node voltage, try to use KCL. So like it is shown here. So we do a nodal analysis by using the KCL at node 1. We can use this should be now easy. You can get this equation, then you will get this equation number 1 from the one nodal analysis. Then you do the second nodal analysis, you get the equation number 2. Then similarly, by doing the nodal analysis as node 3, you will get the equation 3. So now you have 3 equations, linear equations, and now you can use the substitution method. Okay, and you can use this method to get the solution. Like for example, if I have 2 equations, I can use the substitution for x as c1 minus b1 y by a1, and then substitute it in second equation to get the y. So this is one way. Similarly, if I use KVL, then I need to have a loop currents, like here it is I1, I2 and I3. Similarly, following the loops, 3 loops, I will get 3 equations, like here it's equation number 1, equation number 2. Similarly, you can write equation number 3 as well by using the third rule. So now the substitution method for three equations will be cumbersome. It may need a lot of equations. So what we do is we try to use another method that's called as a Cramer's rule. So if you have three equations of this form, a1x plus b1y plus c1z equal to p1, and another one is a2x plus b2y plus c2z is equal to p2, and a3x plus b3y plus c3z is equivalent to p3. So then you can use the Cramer's rule, which states that find first the determinant, that is delta, of the constants, coefficients. So you will have a determinant of a1, a2, a3, b1, b2, b3, c1, c2, c3, and then you find delta 1, delta 2, delta 3. Delta 1 is found by replacing the first column by the right hand side constants, and similarly delta 2 by replacing the second column, and delta 3 by replacing the third column. Then you can find the variables like here x as delta 1 by delta, y is equal to delta 2 by delta, and z is equal to delta 3 by delta. So this is how you can find the variables. Okay, so this question, what is this question here? Problem here is that you need to find a DC voltage, assuming that the capacitor is shorted for the input signal frequency. So when I apply input signal frequency, we had to assume this capacitor as a short. Okay, so it's the frequency operation is such that it is after the pole. Okay, so now I need to find the output voltage, that is right here denoted by this red circle. I need to find this voltage. Okay, so that this is very simple. For DC, the capacitor behaves as an open, so it blocks the signal, and for AC, it feeds the signal as a short signal. So I need to find this V0. It's pretty simple. You have 50 ohm, 50 ohm. This will be open. So this is the voltage across this 100 ohm total. So it will be 100 divided by 500 plus 100 multiplied by 12. So this is equivalent to 2 volt. Okay, now I need to find the AC part. So for the superposition principle, if a circuit is like this, uh, I can use a superposition of the DC, and on top of it I will get an AC. So we calculated the DC part in the previous slide, that's 2 volt. Now I need to calculate the AC part. So this is my circuit. The 50 and 500 ohm will be in parallel for AC, and I will get then from the voltage divider V naught as R dash divided by R dash plus 50 multiplied by V in, where R dash is 50 parallel 500. Simple. So you use the superposition principle in this network analysis. Give me a second. Okay, so uh, this is a question on the diode. We'll discuss what diode is. So in the forward voltage for this ideal diode, we consider that the diode is short, and for the reverse voltage it is open. But from the figure we see that in one cycle, when the V in is in positive side, D1 is on, and when it is in the negative side, D2 is on. Okay, so V naught will follow the V in. So diode is a PN junction, like shown here. So P side, P type on left hand side, and here N side is N type. Sorry, right hand side is N type. So you have a lot of electrons on the N side and a lot of holes on the P side. So what happens is when the materials are connected, the electrons will transfer from N side to P side, and then a potential that's called as the built-in potential is gets developed, which further stops the transport. So this is the band diagram. So you may have seen this, and this total potential from this to this is called as a built-in potential. Okay. So you have electric field in this direction. Electric field is always in the direction of increasing slope. So when you have electric field in this direction, if for example electron is here, it will tend to go down. So this is where I had shown what happens when we apply the voltage. If we apply a positive voltage, since it's a band diagram, band diagrams are drawn with taking into account the electrons. So when you apply the positive voltage, the bands will go down. Energy is minus EV, and when you apply a negative voltage, the energy will increase. Okay, so this is again from the diode. Okay, so this is important how to solve this these type of problems. So you have voltage V naught across the diode, right? So the total current flowing is 4 minus V naught by 1K. And this is my diode current equation. ID is equal to I naught exponential of ED by eta minus 1. And if I uh, if I consider that the diode is on, I can ignore this one. So I can write ID by I naught as exponential of E naught by VD by, or V naught or VD by eta VT. Okay, so what is step one? Step one is consider the diode voltage to be equivalent to 0. Then you can consider ID as this value, and then from this value you can calculate VD, which is simple by given by this equation. VD will be ln of ID by I naught multiplied by eta VT. Consider eta is equal to 1, you can get VD. Similarly, you repeat these 3 times, and you will get the final equation. Okay, let's move on. So this was it from the. Okay, so in the next week, uh, we discussed on the BJT. We discussed on the BJT, and the problem here is that we need to find the transconductance. So the transconductance is given by this formula, DIC by DVB, DVBE. For the circuit shown in figure 2.1, identify the correct IV characteristic from which the small signal transconductance is calculated. So we need the output current and input voltage. So option number C. So this is a model which is used to calculate the BJT current. From the KCL, it's understood that emitter current, which is the injection current, supply current, it should be equivalent to base current plus collector current. Okay. Then we discussed on finding the output resistance for the BJT. Okay. So this is the characteristics of an ideal BJT, and there is no base width modulation. So your VA, that's early effect voltage, is very large. Here I have written it's infinite. But what if there is a large base width modulation, then you can get a very low value of VA. And R naught, R naught is calculated by 1 by lambda IC, and lambda is 1 by VA. So higher the VA, larger the R naught, and that is good for your circuits and gain. Okay, so rest is the numerical which you can do. And here the important thing was beta. Beta is IC by IB. Alpha is IC by IE. Simple numericals. Then we discussed slightly on MOSFETs. What is a MOSFET? It's a metal oxide semiconductor field effect transistor. And this is the model which is used at very basic levels to calculate the drain current going through the MOSFET. And it's given by mu naught Cox W by L multiplied by VGS minus VTH, VDS minus VDS square by 2. And when in saturation, it will reduce to mu naught Cox W by 2L, VGS minus VTH whole square. Like here. Okay. So let's have a repeat on NMOS operation. So substrate is P well, and these drain and source are highly endowed to create the ohmic contacts. So when the VGS is negative, when you have a gate source voltage very negative, the accumulation of positive charge occurs, and this is called as the accumulation state. And when it's slightly positive, there is a depletion, so there will be negative immobile electron charge here, which is called as depletion. And then when there is the gate voltage which is very high, then you can introduce the inversion in the P-well at the surface. Similarly, for the PO and PMOS, it's opposite. You can just look at it. So this is the same. Okay, let's just have a quick look on this problem. For the circuit shown in figure 2.9, consider KWL mu1 is mu1 Cox, and KWL1 is, sorry, these are equivalent to each other. And it's equal to 0.5, and similarly KWL2, both are NMOS. Its second one is 2 milliampere per volt square. VTH1 and VTH2 are equivalent to 0.4, lambda is 0. Find the DC output voltage, and that is V0, such that both the transistors are operating in the saturation. Okay, so the first thing first, when the transistors are connected in a series, so you have a current of ID1 and ID2 flowing through them, and which should be equal. And this will give us a TC point. Here V0. So we have two values. V0 is equal to 0.8. V0 is equal to 1 volt. So V0 when it's 0.8, VGS2 will be 1.3, which is this volt, minus 0.8, it is 0.5, and it's greater than 0.4. So why is 0.4 important? To keep the device in saturation. Okay, so this is what we discussed in week 2. Again, the week 3 started with BJT, and the important things here, let's say beta, which is already known. So let's not discuss this. Okay, so this is one important thing. Here it should be IC. So transconductance is output current by input voltage. So you will use this formula. And output conductance, which is the output current, change in the output current, there will be change in the output voltage. So if I use this formula for collector current, IS exponential VB by VT, GM will be IC DIC by dVB, which is given by this equation, and it is equivalent to IC by VT. So transconductance is given by IC by VT. Okay. Similarly now R pi. R pi is the input voltage by input current, like here. Now if I multiply and divide by IC and IC, then input current is IB and IC by IB is beta and IC by VN is GM. So R pi can be calculated by beta by GM. So this is very important formula. You can use it anytime. Right? Rest is the same. R naught we checked, it's 1 by lambda IC or VA by IC. Okay. So then we studied how to draw the equivalent circuit. Let's say this is the circuit for which we need to draw the equivalent circuit. So first we have a input voltage, then input resistor, then R pi, which is intrinsic to the transistor, and then we have the base, which is grounded, and we have GM VBE. GM is the transconductance, VB is the forward bias base emitter voltage, and R naught is the intrinsic output resistance, and RC is the load resistance, output resistance, collector resistance. So if you have to find the gain, what you will do is you will find a KCL at V0. So it is V0 divided by RC parallel R0 plus GMVBE, and why you can get the V0 as minus GM RC parallel R0 times VBE. Okay, and then you have GM, you can substitute it here and you can use this for the problem. Okay, so if I see something important to discuss, this is again same for the MOSFET. Here you can use, since we consider this as input resistance, and nothing goes here in terms of DC. So 20 and 20 ohm are in parallel, you can get the VG voltage by using the voltage divider. So that is the important step. Okay. Now one more important concept, and that is the calculation of resistances in any circuit. So let's say you have this block with resistor R. You want to know what is the resistance. So what you will do in the lab is you take the voltmeter, you take the ammeter, so you connect it in ammeter in series, and you apply some battery with a known voltage. Then if it is a known voltage, then you don't need voltmeter separately. So you supply that voltage, you check the current flowing, that's I, and you have also the in series the resistance block with the resistance unknown resistance are connected. Then you check the current flowing, then your simple formula V is equal to IR. So my resistance will be V by I. Okay, so if I have to calculate the input resistance here, so I will connect a test source of Vx Ix, and here from the circuit Vx is Ix times 10k plus 10k, therefore Rn is 20 kilo. Similarly, you can calculate the output resistance. You connect Ix and Vx, and Ix will be Vx by R plus GMVI, and Ix will be, since input voltage will be 0, then Ix is for Vx by R. Okay, so this is simple. Okay, let's see what we discussed in week 4. Give me a moment. Okay, so as I said, for the coupling capacitors, the C1 will be shorted at lower frequencies, and others capacitors will be shorted at very high frequencies. So we'll check that how to calculate the ports. So you can use this equivalent circuit. You should be able to draw this now. We have drawn equivalent circuits throughout the course. Okay, now if you have to calculate the gain in dB scale, so if you use voltage, then you need to use 20 log AV, and if you use power, then you need to use 10 log AP. Voltage gain in dB is okay. Input output resistance, again we know how to do this, and this is the equivalent circuit at the test source and then calculate. Okay, so this question will give us a repeat on how to calculate the poles. Okay, the question is find the value of signal coupling capacitor C1 such that the lower cutoff frequency of the amplifier is this. Omega is given. Now we need to find the value of omega. So what I will do is I will find the input voltage going into the transistor. That will be given by this formula right here. Okay, and also I have voltage, output voltage in terms of PN as like this, which is completely found using the ACL at output node. So once you solve this, you will get an equation of this form. Okay. So now pole is when the denominator, magnitude of the denominator is equivalent to 0. So here that happens is when magnitude of first term, that is this and this will be 0. or they will be equal. Okay, so you get a C1 from this equation. Okay, in this question, we need to find the maximum output signal swing without significant distortion. Significant distortion means we need, if we supply a sinusoidal signal, we should get a sinusoidal signal at the output. That's what without significant distortion we need. So first we need to find the Q point, that is the DC analysis. So we got the Q points as V0 as 3.2. Now if this V0, okay, okay, right. So we have this VDC sat of 0.2. So if I apply KVL now, this will be 10 minus 0.2 minus this is 3.2, so it should be 6.6. So I can have a cushion of 6.6 volt in the above, below which I can get a signal without disruption in the positive side. And similarly, V0 can go to 0 and there won't be any distortion. So the voltage swing is 2 into minimum 1. Minimum is 3.2. Minimum of 6.6 and 3.2. It should be total 6.4. Then you can now you can find the V input swing as well. We know the V out is gain times V in. V in swing will be V out swing by gain. So V in swing will be 6.4 divided by GMRC. GMRC is the gain. Then on the question on the MOSFET, so which again the BJT is a simple problem. It's not. Okay, in this problem, we have to find the gain with and without the bypass capacitor CE. With that, so when we bypass it, short it, we get a grounded emitter. When we don't short it, 1 second, I get emitter receipts. So this will be a good practice. I have shown this. You can try it as well. This is simple. You just need a multiple node analysis. Again, the problem on the input basis, which I guess you should be able to do. And this is the formula for the device in saturation. This is again the same. Okay. So in this week, what we had studied was how to compute the input resistance, how to draw the equivalent circuit, and how to find the cutoff frequencies. Very important week. Okay, we will discuss in week 5. Okay, in week 5 we have started from the MOSFET. In this part we have to find the gain, assuming that the signal coupling capacitors are shorted for the input signal. So this is my equivalent circuit. One second. in this problem, we need to find the small signal voltage gain, assuming the coupling capacitors are shorted for the input signal. So this is my equivalent circuit. Now it is very simple. We know by V not BGM nothing. And now we need to find the GM. It will come from this equation of IDS. GM is dIDS by dVGS. And we will get at this equation kW by L VGS minus VTH. VGS will be found by voltage divider. Here we can see it's R2 by R1 plus R2. Okay, so that is 3 volt. Simple. Output resistance, similarly from the same figure, we can get by attaching a test source at the output, we will get the output resistance is RD. Similarly, if you have to find the input, you can add a test source at the input, so you will get R1 parallel R2. Okay, so find the value of the coupling capacitor C1. So the lower cutoff frequency is 10 Hz, so F is 10 Hz. Again, like in the previous week, we had studied about this, how to find it. Same, you find the gain, and then you check the denominator, and you will observe that you will get the equation of this kind, and you equate the two, and you get the 4. This is power dissipation. Power dissipation is simply given by V into I. Okay, this is again on the equivalent circuit. Nothing new. Okay, so one more thing that we can use is to find the cutoff frequencies is like this. For example, if you're a capacitor, if you want to find the cutoff frequency related to the capacitor, what you do is you find the resistance, net resistance on right hand side of it and on the left hand side of it, and then equate add the two, you will get the total resistance, and then omega R equivalent that capacitor is equivalent to 1 or greater than 1, so that will give you the cutoff frequency. That is one trick. Okay, now the Miller theorem. So in this week, what the important concept was Miller theorem. That is, if you have a circuit of this kind, where this is the amplifier of gain A, and you have a Z impedance connected from input to output node. What you can do is you can split that impedance in two parts, one at the input and one at the output. So that is given by Miller's theorem. So if I have this capacitance C mu, which is attached to input and output, I can separate it into two. One is C in, then C in total will be equivalent to C pi plus some part that is given by Miller's theorem, that is equivalent to C mu 1 minus A. Okay. So if I split it, so it will be C1, this will be C2. So C1 will be Cf times 1 minus A, and C2 will be 1 minus 1 by A. Okay, so that was the important concept we studied in week 5. Okay, let's move to week 6. Okay, so we started this week with finding the output resistance. If you have a good hold on this, finding these values, that will help you in money exams as well, like you may appear in GATE. So it should be very easy now for you guys to calculate these, like output resistance, input resistance gain, finding the output capacitances, total output capacitances, total effective input capacitances. Okay, so it should be easy now. Find the cutoff frequencies, find the mid frequency gain. Okay, so for this problem, we need to find the output resistance. So what we'll do, we'll start with again drawing the equivalent circuit. You should have a good hold on drawing the equivalent circuit. Attach a test source to the output and find the R out. So this is my equivalent circuit. This is my equivalent circuit. I will ignore these two capacitances, and I can find the attached test source at Vx and Ix. When a test source is attached, the rest of the sources are shorted. So input will be shorted. So my GMVGS will be 0. Therefore, upper cutoff frequency will be 1 by, as I said, there is a trick. Directly use this resistance across that capacitor. So I will get FU is 1 by 2 pi C out R out. So that will be 1 by 2 pi, and 100 P is my CL, that is load capacitance. We are assuming here that C2 is also shorted, so it will give me 0.4 megahertz. And the first part, I guess this was the cutoff frequency. Similarly, find the gain at this frequency for the circuit, assuming that the parasitic capacitance is same. So we know that gain is GMRD. GM is, you can calculate from this formula, and VG is this. So what is the importance here is that omega is this one. That means your input capacitance will be shorted. So that's why we can use directly this formula. Okay, from the Miller's theorem, we can calculate the effective input capacitance CGD, and the input will reflect as CGD times 1 minus A. It will be in parallel to CGS, so you can get the effective input capacitance. This was mainly there was again the equivalent circuit. How to use the Miller theorem to calculate the input and output effective capacitances. This type of question we already discussed. Let's check the next slide. This is easy. This is again finding the effective output capacitances, and then the cutoff frequencies, calculation of poles, that is the frequencies. Okay. Okay, this is a common yes. So common gate is often used for the switch applications like this. If the transistor is on, no signal passes. If the transistor is off, no signal passes. If the transistor is on, there is a signal passage. Find the value of the small signal parameter RDS. I need to find RDS. So first, it would be important to have all the DC points like here, VS and IST, and R0 is simply 1 by lambda IST. Find the output voltage, find the voltage to the current gain, V out by IN. And for that I have drawn this equivalent circuit, which seems very important here. So you can use this equivalent circuit to calculate the, like follow the nodal analysis, you reach here, and you get IN of this. Similarly, then you can find the cutoff frequencies by using number 1, number 2. Okay. So this is the cascade system. Nothing difficult here. You need to find V0, V out. For that you should have accurate values of VG2. So nothing new concept in this week. Again, finding the equivalent circuit, using the equivalent circuit to find the resistances. Just a recap of the formulas. This is GM by beta, and again the same concepts. We didn't discuss anything new. Same concepts, different circuits. Okay, so this is a differential pair. In this week, we have discussed on the differential pairs. What can be done is you can separate this differential pair into half and then do the half circuit analysis. And for the differential mode, this RT will be grounded. This will be grounded here. And for the common mode, then this will be, and the half circuit will be 2 times RT. Okay, for differential mode, it's important to remember that for the differential mode operation, this VT, that is this potential, it is grounded. Input voltage V drops across the transistor in this RT. Drop across transistor is 0.6 and drop, okay. When you do this, it becomes very easy. This is again the same thing. Okay, this is how the half circuit analysis looks like in differential mode. So you directly ground the emitter. Okay. Here. This is its half circuit analysis. The total gain can be given from the half circuit as well. Here the total gain of is GMRC Vn2, V02 is GMRC Vn. So GM are equal, RC1 R32 are equal, so V0 is V2 times GMRC, and Vn is Vn by 2 in the differential mode, so 2 and 2 cancel, it will be GMRC, similar to the individual ones. Find the common mode gain. In the common mode, you have 2 times the RT in the half circuit. Then it's very simple. You need to find the output. So this is my common mode gain. GMRC divided by 1 plus GMRT. If GMRT is greater than 1, so it will be RC by 2 times RT. Okay, so to find the common mode output signal, that is VO underscore C as V01 plus V02 by 2 for the differential mode circuit. So this is my output voltage. V01 is like this and V02 is like this. So you can get V0C as the average, which comes out to be this. Also important parameters, CMRR is 20 log AD by AC. More the CMRR, a good circuit. Yes. Okay, the current mirror. We will study why we need current source in our circuit. First, why it is important. Advantage of using current source. When we bias the device, we can use 2 types of sources, voltage source and current source. MOSFET. I is equal to KW by 12, VGS minus VTH whole square. This is the equation, standard equation for the MOSFET in saturation. and GM is given by equation 1 and equation 2. So one depends on VTH. VTH thresholds may not be constant in the device, right? So VTH may change depending on the external and process parameters. If the temperature changes, so can VTH. So you have this band diagram. You have EC, you have EV donor level, and you have EV. So what happens is as the temperature change, this donation of the electrons to the conduction band changes, right? So if it changes, then you need to it will change the voltage, threshold voltage as well, because the threshold voltage determines when the channel is when the transistor is on, and that on will be determine how many electrons are in the conduction band. So EF changes as well, it changes the voltage at which the device operates or turns on. So delta T change the concentration of Na, NH, NMOS, and the PMOS. Oxide thickness change, and that is the polar depletion effect, doping. Okay. Now GM dash. If there is a threshold voltage change, it will be given by KW by L, VGS minus VTH dash, and VTH dash is given by VTH plus delta VTH. Just a few steps, and you will get delta GM by GM naught as delta T VTH by VTH minus VTH. So device is sensitive to the threshold voltage change. There may be change in mobilities as well due to temperature. K naught is 1 minus Cox. So GM dash will be like this, and ultimately we'll get delta mu by mu naught. So this is when we use the voltage source. Now using the current source. GM is given by this equation. But VTH dash is VTH plus delta VTH. Since I is fixed, GM dash is 2kW by L. I is fixed, delta GM is 0. Mobility change will be mu naught dash. Mu dash is equivalent to mu naught plus delta mu. GM naught is 2 mu Cox W by L I. So this is my mobility sensitivity. Sensitivity drops to half the previous value. So the device, so this using the current source is more beneficial. Next, we can discuss the current mirror. Initially, let's say the M1 is off. We need a VGS value which is greater than VTH to turn on the device. At first, IS is greater than I1. So what happens is the parasitic capacitance starts charging, like here, CP, and its voltage starts increasing. So once its voltage starts increasing, VG starts increasing. So when VG starts increasing, I1 starts increasing. This process continues till IS is equivalent to I1, and that at that time VG will be some voltage which turns on the device completely. Then the same voltage gets applied to transistor M2. Since this M2 will be identical to M1, so the same current flows through this device. Okay, so this is the concept of current meter. Same is now applied to the problems, and that should be easy to do now. Okay, means device management situation. Okay, so the concept here is small signal output resistance remains high. That means the device is in high resistance state, that is high saturation state. So in this week we have studied about the using the current sources or voltage source, and then also about the current mirrors. Week 11, and in week 11 we studied about the feedbacks. We had a brief introduction on how what is the feedback, what is the feedback network, what is the negative feedback, what are the different types of amplifiers, and based on that we have this few problems like which type of amplifier is this, and uh, which state increase the resistance and which state reduce the resistance. Okay. So like here in this, for example, this is the current sensing. Sensing is at the output, current mixing, it is at the input. So we have this ACL are the input to find IS, and then I know the IS, which is supposed to be called with this part, which is discussed recently, so you should know. Here the input resistance decreases by 1 plus AB. This is called as a desensitivity factor. AB is called as a loop gain. AB is loop gain. Okay. Here we have an increase in output resistance. So the important thing to remember from this week was to uh, be able to judge whether the resistance will increase or resistance will decrease. So that depends on uh, if you are taking current that is a series connection, so that will increase the resistance at the output, and if you are mixing it as a current at the input, that will be a shunt connection, that will decrease the resistance at the input, vice versa. So if you are taking the voltage, that will be the shunt connection at the output, so that you are reducing the resistance, and if you are adding the voltage at the input, that will be a series mixing, so that will be increasing the resistance. So in the last week as well, we continued this using the feedback networks. For example, here we have to find the VS. So we'll just use the similar voltage laws, KVL and KCLs to get your answers. Pretty simple. Output resistance, now including the feedback as well. Like here you get output resistance which gets reduced. So you should know already before going to the conclusion. You should know already whether it should get reduced or increased. Also, this was important. Which type of feedback is this? So you are seeing here the current flows here because it is in the series, so it is a current sampling, and it's a series mixing because it's a voltage mix up. So if it was a shunt, so it would have been shunt. Okay, let's go to these theoretical questions. To obtain the low input impedance and low output impedance in amplifier, which topology is mostly used? As I said, low impedance depends on taking the shunt connection. So you take the voltage at the output and shunt series mixing at the input to get the low input and output impedance. Similarly, in comparison with the basic amplifier in the series, so your series that is taking current at the output. So first one is always the output, and series input is the voltage. So it will be low impedance at the sorry, high impedance at output, high impedance at the input. Similarly, you can answer this one: voltage series, low output impedance, high input impedance. Okay, for this part as well, voltage control current source. This is a simple basic amplifier. So ZI should ideally be infinite such that the whole voltage drop appears across it. And similarly, Z0 should be infinite such that the whole impedance, whole voltage gets applied across Z. Again, this is again taking in the shunt. So this will be voltage, and it is taking the current value in the shunt, so it is a voltage. So overall, we started this course with KVL and KCL, then with the diodes, then with the BJTs. We discussed MOSFETs, we discussed current mirrors, we discussed Miller-Thurm, we discussed how to calculate the resistances, output resistances, input resistances, how to calculate the cutoff frequencies, and then we discuss the differential pair amplifiers and also the current mirrors and then feedback networks at last. And I hope that the sessions were of some use to you guys, some of you guys who watched the videos and took notes. And let's see if we can get some another course in the next section, next semester. Thanks. If ever you need any help or you have any doubts, you can always comment in the video section or you can reach out to me.